Yeah, well, so first, off the top, just my apologies for not being there with you in person. I was certainly hoping to come and put some faces to names, but I was keeping tabs on the weather forecast and felt like it was unlikely I was going to both get to Vancouver and then back to Victoria today. And as it turns out, I would have been joining you anyway, even if I had made that plan. So thanks for accommodating me by phone and just letting me share the screen. So I'm the Deputy Director at Clean Energy Canada, and we're a think tank based at the Morris J. Wask Centre for Dialogue at Simon Fraser University, so in downtown Vancouver, but we do also have offices outside of Vancouver, including here in Victoria. And being housed at the Centre for Dialogue, one of the approaches we use in our work is dialogue. And so I just wanted to say that I'm very impressed and encouraged at the approach that FNCI is taking, which is a dialogue-based approach of, unlike in so much of our discourse right now, which is yelling at each other on social media, through the media, in the political arena. It's very encouraging that there are fora like this that are being created where people will actually listen to each other. So very, very happy to see that approach being taken, and it's one that we use as well. So our focus is on clean energy and its relationship with climate change as a solution to climate change. And our role is to conduct research, both in terms of policy solutions, but also trying to keep track on technology trends, market trends, and then ultimately provide policy advice to governments as to how to put in place policy that's going to reduce emissions, clean up our energy system, and create economic opportunity in the process. Starting with the premise that a global energy transition is underway. And this is a diagram that I find is a quite useful illustration of the cycle that our energy system has gone through multiple times through history. And it's a diagram that was in Peter Tertsakian's book, 1,000 Barrels a Second, which was published, look at that, 14 years ago. So quite some time, and there's been a lot of discussions about this, thinking about this in the Canadian context. But I think it's really now coming to the fore, and that's because the energy transition that is now underway, for example, with the shift from coal to gas in electricity, particularly in the United States, in Europe, in Canada, and increasingly in Asia. That's one piece of it, but it's a much broader transition that's afoot. And it provides us with an opportunity to resolve some really big global challenges and domestic challenges. So, energy access to the more than 1 billion people who currently lack it, meeting demand for more than 3 billion people over the course of the next 40 years, delivering that energy at an affordable cost and with both a lower carbon and emissions footprint. We also have some of these challenges within Canada when it comes to energy access, particularly in remote and northern communities. So this isn't just a developing economy challenge. It's something that we're confronted with here at home as well. And if we look at this cycle, over the past 100, 150 years, we really had growth that was driven by or sustained by a dependency on fossil fuels, on oil, gas, and coal. Over the past couple of decades, we have seen this buildup of pressure, environmental forces, geopolitical forces, social forces, policy and politics, business, innovation, and I think really it's been over the past couple of years, some people would point to the Paris Agreement as something that's precipitated somewhat of a breaking point in terms of there being, from that point forward, a lot of policy action coupled with consumer preference, coupled with some fairly significant strides in innovation and deployment of clean energy technologies that have precipitated this shift that's underway and that's taking us towards a rebalancing. And that rebalancing will be a system that probably doesn't resemble the system that we came to know over the past century or so. It's going to look significantly different. And when we look historically at energy transitions, They typically happened over quite long periods of time, and they typically haven't had as much government or policy intervention as we're already seeing in this transition. And that's because there wasn't ever anything as significant in terms of an existential threat like climate change precipitating that kind of intervention. Now, in terms of how fast this transition unfolds, I just want to point out that one of the other big differences is that historically, we tended to be just looking at fuel changes or maybe swapping out some of the hardware, how we use that energy. What's different about this transition is we're also now layering on top of that software and the power of being connected, Internet of Things, the power of software, and the amount that we can do by virtue of having all of this data and having this network that allows us to take things like fuel shifting, take things like different types of hardware, and amplify the impact that those have. So there are a lot of different scenarios, forecasts that are put out there by the International Energy Agency, McKinsey as one consultancy. There are numerous others. I've chosen to use the McKinsey projection because I think they actually present it in a way that is quite accessible. And I think a lot of the insights that they've drawn to inform their scenarios are quite aligned with what we're seeing in the marketplace in terms of cost changes for technologies, what we're seeing from a policy response perspective. And so I'm going to share a few slides of their reference case, which is the world as they see it unfolding based on the current policies and political or policy landscape that we've got globally. And so some of these forces that have already been put in motion, but it's not presuming that we're seeing more policy action than what's in place today. So in a sense, a business as usual view of the future. And so even in this reference case, there are a few things that stand out. So one is that global primary energy demand plateaus after 2035, and that's despite population expansion and economic growth. Two is that electricity consumption doubles until 2050, and renewables are projected to make up more than 50% of generation by 2035. Third is that gas continues to grow its share of global energy demand, and so that stands in stark contrast to what they're projecting for both coal and oil. With oil, the demand growth slows down substantially and peaks in the early 2030s, and carbon emissions are projected to decline in large part due to the decrease in use of coal, but this still isn't putting us on a trajectory towards limiting climate change to 2 degrees, let alone 1.5 degrees. So I wanted to dig in specifically to look at, well, what does this mean for fossil gas? Obviously, this conversation is in part premised upon the opportunity of gas and LNG and what that could mean for BC. And so what we see is that by 2030, new build renewables will outcompete existing fossil fuel generation on energy costs in most countries. And so McKinsey flags this as being one of the real key tipping points in the energy transition. And they also see the majority of countries reaching that tipping point in about the next 5 years. Even then, we do see a lot of additional gas being added to the grid, particularly in North America and the United States, and Mexico, as well as in China. And so some fairly significant growth looking out to 2035. And the reason for that is, well, there are several reasons. So one is that in this reference case, they are seeing increased electrification, especially of transportation with adoption of electric vehicles. So we're seeing significant growth in demand for electricity. We're seeing a lot more wind and solar coming on the grid. But then that's where the role of gas is providing both some baseload, but even more importantly, that dispatchable ability. So if the wind isn't blowing and the sun isn't shining, that's when you fire up your gas generation to make sure that you can balance your grid and everybody's got power when they need it. So what they project is that we have this fairly sustained growth out to 2035, and then it really plateaus and just begins to start to taper out towards 2050. But as I said, the big caveat with this projection, and as is illustrated quite starkly on this slide, is that when you look at the amount of emissions associated with this reference case and with the nature of the energy system, it's inconsistent with either a 2-degree pathway or a 1.5-degree pathway, and very significantly so. So McKinsey also models what an accelerated transition would look like. So they make a variety of assumptions of things that could happen that would accelerate the reduction of emissions. It's still not enough to hit the Paris targets, but based on things that when they look at what's happening with technology costs, the prospect of additional policy, what are some of the other things that could be achieved? So you can see here that they look at things like efficiency gains, faster uptake of low emission fuels for aviation and marine, accelerated electrification, particularly of residential heat, more use of electricity in low and medium temperature heat, industrial processes, faster cost reductions for renewables and energy storage, and then also increased electrification, which means even more power demand. And when they put all of those pieces together, what they find is that we actually end up with an even greater demand for natural gas than in the reference case scenario. And that's largely tied to that increased demand for power because of electrification, an increased amount of wind and solar on the grid, and the need for gas to play that balancing role. So I think one of the questions is, in both their reference case and their accelerated transition case, which achieves still not adequate emission reductions, but deeper emission reductions, there is very obviously a need for gas. As I said, mostly because of increased electrification and the ability that gas can play, the ability of gas to serve as providing that balancing capacity for those variable renewables. But one of the things that's flagged is that any kind of a breakthrough in seasonal energy balancing technology, so hydrogen, pumped hydro, big batteries, and that changes the outlook significantly. All of a sudden, gas demand in 2050 is relatively, relative to those other two scenarios, it would be low. It would be roughly at today's level. So what we need to look at, if we go to the next slide, and what we need to be keeping an eye out for are disruptors. And so the IEA, the International Renewable Energy Association, McKinsey, others have all really pointed to the prospect of developing cheap hydrogen, and whether that's blue hydrogen, so producing hydrogen from natural gas with steam methane reformation and capturing the carbon, or whether that's green hydrogen, which is produced through electrolysis, so using electricity to produce hydrogen. They've all pointed out that because of its relatively high energy density, it can be used as an energy carrier in almost all sectors and a wide variety of applications in transportation, in buildings, for heat, in the industrial sector, as well as being useful for short or long-term storage in the power sector. And if you add all of those together, it could prove to be a significant competitor to natural gas. And the reason why I think it's important for us to bear this in mind is not to throw cold water on the prospects for exporting LNG, but in part just, I think, as a reminder of that, we ought not put too many eggs in a single basket. And I think, unfortunately, that's been part of the history of resource development in Canada, is that we tend to put a lot of eggs in a single basket. And particularly when we look now at the rate of change, particularly in the energy sector and the energy transition, I think that's a fairly risky proposition. So one of the things I wanted to do is to also just paint a bit of a picture of some of the opportunities that are unfolding with the energy transition here in Canada from an economic perspective. So if we go to the next slide, just going to share some of the results from a study that we released last October, where we worked with Navius, which is a energy and economy modeling outfit based in Vancouver. We used their GTEC model to look at if we take the policies that were in place as of February of 2019, the climate policies, both provincial and federal. How are those going to shape our energy system in Canada, and how are they going to shape the economy as well in terms of investment, GDP contribution, and jobs? So when we did this with Navius, we scoped the clean energy sector quite broadly. So I think a lot of times when people hear the term clean energy, they really just tend to think about the supply side, and even then they really just tend to think about wind or solar power. So we've scoped this quite broadly within the context of both how we produce energy and how we consume energy in a way that is consistent with reducing our greenhouse gas emissions. So quite a few different sources of clean energy supply, including emissions detection and control, which means things like carbon capture and storage, grid infrastructure and energy storage, so how we're moving and storing that energy. And then on the demand side, we looked at the different ways that we consume energy and can consume less energy in both buildings and transportation. Unfortunately, there wasn't suitable data for us to model this out for clean industry, so that's one sector that's not included in this analysis. What we found is that over the course of the next decade, the clean energy sector GDP is set to grow about 3.4% every year. So that would take it from about $55 billion in 2020 to on the order of $77 billion in 2030. Compared to projections for the Canadian economy overall, that's a significantly faster growth rate. Similarly, the number of the jobs is also set to grow about 3.4% per year as well. So that would take it from about just under 400,000 in 2020 to well over 500,000 in 2030. And again, so that's a significantly faster job growth rate than what we expect in the rest of the economy. And in part it's because we would see investment rise in the billions, so 28 billion in 2020, rising to 38 billion per year by 2030. So one of the things that the analysis also showed is that while the fossil energy sector continues to grow as well in terms of GDP contribution and investment, one of the observations is that growth is being accompanied by fewer jobs. And so we actually see lots of jobs in the fossil energy sector. But one of the things that I think provides some solace is that with the rate of growth in clean energy jobs, we do see a net increase of 110,000 jobs. Now, this isn't to suggest that clean energy is better than fossil energy, or all of those people who are losing their jobs in the fossil energy sector could assume one of those clean energy jobs. But one of the things that we want to achieve in the discussion about energy in Canada is to actually think about our energy sector in its entirety, so both the clean energy sector as well as the fossil energy sector. Now, if we go to the next slide, I'm actually going to take us away from the clean energy sector explicitly and just share some of the other work that we've done where we've been looking at how the global energy transition can create broader opportunities for Canada and for BC as well in our natural resource sector. And so a few years back, we did an analysis where we were looking at the mining sector and how it stands to benefit and see significant growth because of the demand for metals and minerals that are used in clean energy applications. And so we focus specifically on solar panels and the metals and minerals needed, but the analysis is similar whether we're looking at wind turbines or electric cars or batteries and other forms of energy storage. So what we found is that 14 of the 19 metals and minerals that are needed to build solar PV panels are in fact found in Canada. And this has been acknowledged by the federal government and provincial governments in the most recent mining strategy that was released. There is an explicit acknowledgement of the opportunity that clean energy metals and minerals provide for Canada. What we see, and this is a map that comes from Natural Resources Canada, is that BC is actually a hotspot of mining activity of clean energy enabling metals. So mines, processing facilities, and advanced exploration projects. We see in particular with copper, lead, zinc, with quite a bit of activity in British Columbia. As we saw on the previous slide of the map, quite a bit of copper activity, and copper really is one of the central metals of the clean energy transition, in part because of the big focus on electrification and having to move electrons. So ultimately, this means that there is opportunity that just a few years ago, mining communities in Canada didn't have a very optimistic outlook, and I think that's changed in part because of the prospect of being able to produce some of the metals and minerals that go into these technologies. And I think it also serves to shift the public perception of the mining sector. It's a bit incongruent to be a big supporter of these clean energy technologies and not acknowledging that we're actually going to have to produce the metals and minerals that are needed for them. Of course, when it comes to the footprint of mining, there are a wide range of environmental impacts that need to be addressed, and one of them, of course, is also the energy used and the greenhouse gas emissions. And what we've seen in Canada and globally is both a shift towards electrification and a shift towards using renewable electricity. So here in Canada, we think there's a really interesting opportunity, much as with the discussion around LNG, is can we be the cleanest producer of some of these metals and minerals that are needed for the clean energy transition. And if we go to the next slide, there's also a question around, is there an opportunity to gain market access, market advantage, or even perhaps fetch a price premium for being able to produce those metals and minerals in such a way. And the last slide, just a few takeaways from this, or a bit of a summary. We have this energy transition, it's underway. I think the outstanding question is really how fast it will proceed. And if we look at the prospect of increased efforts to limit climate change to 1.5 to 2 degrees, the transition is likely to accelerate. Now, within this transition, there's a role for gas. I think, again, the question is the scale and the duration of that role, and it's going to be a function of the scope of climate action. And again, the prospect of there being disruptors and competition from lower carbon resources and technologies. The transition presents us with a diversity of economic opportunities. And again, this comes back to how many eggs do we put in a single basket? And certainly when it comes to the role of government as policymakers, as well as providers of significant dollars going into infrastructure, there's an opportunity cost. And so from our perspective, a diverse approach will serve to maximize the economic and environmental benefits while minimizing the risk of stranded assets or foregone opportunities. I will leave it at that. Happy to take some questions.
But, it comes back again to the need for coordinated policy development because, if you look at, say, one of your examples, there was, a resurgence in copper mining might be an outcome of this shift. Well, it can take 8 years to permit copper mine. So what policy changes do you need to make to allow that shift to take place most effectively? I think we have a very efficient and effective mining sector that could claim to be amongst the best in the world, but what other policy changes need to take place in coordination with the policies that are involved in other aspects of the energy transition? So back to governments again, and all those people who participate in the policy development process. It needs to be coordinated at a level that perhaps we're not currently used to.
Yeah, I think it really does boil down to that question of coordination, obviously, between government and various sectors of the economy, and obviously, communities and nations within British Columbia. It also comes down to coordination within government. And I haven't seen the economic strategy that Vaughan Palmer has seen, and it sounds like some of you have seen, but I'll be very curious to see how much coordination and integration there is across these different opportunities, and the extent to which they are actually bundled up in a way where we could tell a coherent story to the rest of Canada and the world about how British Columbia's economy is evolving in a way that's consistent with climate objectives and is consistent with the energy transition and is actually enabling or accelerating the energy transition and the reduction of emissions both in BC and beyond our borders.
Yeah, I just had going back to the McKinsey analysis. Well, number one, thanks for the presentation. I thought it was a great presentation, especially bridging over into the mining component and the resources needed for the energy transition. Going back to the McKinsey piece where they did some modeling looking forward, and as modeling goes, many assumptions and inputs. But I think that one of the pieces that was missing in that analysis, which was captured in the IEA report of this fall, is the gas, as the gas grows and then even flattens out. The big story is where is the gas needed? And so we have this abundance of natural gas in North America, and what we have is a pretty steep decline in gas use in North America as we look into the future, but a very strong growth in gas demand in Asia. So the story becomes getting the gas to the places that need it. And how do you do that? Of course, LNG becomes a big part of that story. So that part is missing. So yeah, maybe the gas plateaus in 2035, but the big part of the story is where you need it shifts from North America to Asia. And we need to think about how we get the gas over there, and that's the LNG story.
Yep, I don't disagree with that. I think, I've been watching China, over the last couple of decades and the evolution of their industrial strategy and their economic strategy and environmental strategy and their energy security strategy. And one of the things that I keep wondering about China and right now we do look at these projections for gas and they're out there, they're trying to buy gas. But when we think about the role that they played in really scaling up production and deployment and the decreasing cost of solar panels, of wind turbines, of electric cars, I suspect that they have a vested interest in trying to minimize their demand for gas and the extent to which they'd be reliant upon imports and finding a potential substitute. So I think one of the things to watch is hydrogen, the role of hydrogen broadly, but also how China is approaching hydrogen and is there an opportunity for them to do the same thing for hydrolysis, electrolysis, that we've seen them do for wind, solar, batteries in terms of scaling up that production, bringing down those costs through deployment, and playing a disruptive role not only in their domestic economy but also on the global scale.
Yeah, maybe just on that one, I agree that they will look for other sources of gas if the gas becomes too expensive, imported as LNG, for example. And they also might turn to their primary resource, which is coal, and then start gasifying coal and putting that gas into the pipes and then sending it to the cities along the coast that they're trying to clean up. But of course, what that ends up doing is displacing the CO2 to those gasifier units, and that is even more CO2 intensive than coal-fired power. So that's also a risk that we might see from China.
Yeah, definitely.
Dan, could you, I'm thinking about the record of these discussions and the constant challenge of translating fairly sophisticated concepts into information that's digestible by folks that aren't familiar with them. So you mentioned blue fuel, and this is a broader question too, also for you, Chris. The way in which gas might be combined with biofuels to create new sources of energy that are less carbon intensive. Can I just ask both of you to re-explain what you meant and explain it to me as if I haven't got a freaking clue what you're talking about?
Dan, do you want to go first?
I was going to ask Chris to go first. Well, I mean, I'll take a crack at that as it relates to the different ways that we produce hydrogen. So right now, one of the ways that we can produce hydrogen is essentially just trying to separate the hydrogen molecules from molecules of natural gas, of CH4. Right now, the way we do that process releases carbon into the atmosphere. And so there are greenhouse gas emissions associated with that. The production of blue hydrogen is the same as that, except that you are capturing the carbon pollution before it goes into the atmosphere and storing it underground. So you're eliminating that issue. The other way that you can do it is through electrolysis, so using electricity to split water molecules and to capture that hydrogen and use it. And so in the context of British Columbia, where we've got a very clean electricity grid, we can do that with virtually no carbon pollution going into the atmosphere. And of course, these different technology approaches have different costs associated with them, and there are different approaches in terms of the way that it's actually done and the amount of energy it consumes. But I think that's hopefully a slightly simpler explanation about that. And Chris, feel free to, or Tyler, I mean, you've worked in this as well. If you've got a really simple way, have at it.
That was good. I just want to ask, so what do we do with the hydrogen?
What can we do with the hydrogen? Is that the question?
Yes.
So we can use it in a number of different applications. So people have probably heard about hydrogen fuel cells, which can be used in different types of vehicles, all the way from passenger cars through to big trucks. And so it's basically, instead of using gasoline, you use hydrogen as your energy carrier in a fuel cell. And in that application, when it the energy is released, and then what comes out of the proverbial tailpipe is water vapor instead of carbon pollution with a gasoline vehicle. So you can use it in the transportation. You can blend it in with natural gas to reduce the carbon intensity of your natural gas. So you can put that into your gas distribution network, and up to a certain point, you can use it in your furnace or in your gas stove without having to make any changes. And then you can also use it in some industrial processes like steel making. So those are a few different ways, and Chris can probably expand upon that.
Yeah, sure. One of the interesting, there's two safe ways to, hydrogen is highly corrosive and explosive. The stuff's just dangerous. It needs professional handling. There's two safe ways to move it. It's as ammonia, where you under light pressure emulsion, it turns to a liquid, you tanker it, or you leave it in the methane and move the methane and then extract it where you need it. Methane's just a very useful molecule. You can basically make syngas out of methane. You can make almost any other hydrocarbon, any more complex hydrocarbon. It's just a very useful molecule as long as you're not leaking it to atmosphere. And it gets better once the carbon source is not coming out of the ground. Effectively, it's fossil source. So you start with captured CO2 from other sectors, combine it, make synthetic CO2. You perhaps use direct air capture someday. You use biomass. When you gasify biomass, so you heat almost any sort of biomass source up to a certain level in a non-oxygenated environment. The biomass comes apart into all these hydrocarbons, and a lot of them are very carbon heavy. And if you've got a hydrogen source to bring together with that carbon, you've got a very, very large source of potential synthetic methane and biomethane, what have you. And we know how to do this in a laboratory on a small scale, but nobody's put the necessary money into it to commercialize it at the refinery level. So it's something we know how to do. It's basic. It's 1880s chemistry, but something that we haven't gotten to yet. So that's kind of building. I was trying to build on what Dan was saying. Now, the one thing you got to be careful with here, it comes back to the corrosive nature of hydrogen, and this comes back to being net zero ready. This project's relatively advanced, but in the future, if it was possible, if you could reline the pipe to handle any mix of CO2, CH4, so any mix of methane, syngas, or hydrogen, you're building a pipe that can operate almost indefinitely as an industrial chemical source. And you can make syngas mixes of CH4, methane, carbon monoxide, and hydrogen, and manipulate them and extract parts of it and use it as energy.
Is it more or less corrosive than, say, sulfur?
Sulfur is much more corrosive.
Because we have pipes that will handle sulfur, so it's
yeah, it's just it's the type of steel we've been using corrodes on contact with too much hydrogen.
Can I actually just
jump in, please?
Because corrosive is hydrogen stress corrosion cracking that you're referring to, and it's not corrosion in the conception of chemistry. It's not a chemical reaction. It's the hydrogen molecule is so small that it actually penetrates into carbon steel, and that's what lifts it. And so and I don't disagree with the concept of anything we've said, but we talk about moving hydrogen in a natural gas pipeline, in a high pressure natural gas pipeline. You can do it to a degree.
Yes.
So these things all have boundary conditions.
So what's super interesting right now is that a lot of the European gas companies, the new pipe that they're putting in is fully hydrogen capable. So the Russians, their new pipe going into Western Europe can take 100% mix of hydrogen. They're designed initially for methane, but they are designed to eventually handle full hydrogen. So I don't know if they change the steel chemistry or they put a plastic liner in, but they're being designed for that.
Yeah, certainly we've heard that on the distribution systems, which are low pressure.
This is the main stem, Nord Stream.
Yeah, we haven't seen that yet.
Yeah.
So.
Yeah, it's cheaper to do at the distribution level. It's cheaper to do plastic pipe. It's been the standard for a while, but it's the big main stems making them hydrogen and syngas capable. So this is kind of launching off.
Okay, so let me bring it back a little bit.
Yeah.
That's super interesting. So help me connect the dots a little bit. So we have, let's say, something like the FNCI scenario falls into place. A new pipe to CNS area and a facility or two there that is now or initially an LNG facility.
Yes.
How does that relate to the opportunity to do some of the things that you're talking about, assuming we fully electrify that?
Yep.
So the electricity's there. There's certainly lots of biofuel around. And how do we put those things together in a way, and that location in a way that enables the energy transition so that infrastructure gets redeployed in a slightly different way?
No, this is where the transition planning the vision I was talking about comes in earlier, an adaptive vision. So, you're starting with LNG, but part of this is you're getting better transmission into the region, which increases the potential value of wind on the North Coast, because, if it's got a surplus, it can sell up into the system, and we can hold back demand dams and run on that wind instead of the dams, right? So you've got another business opportunity that happens there. Now, once you've got the excess renewables capacity, the high voltage transmission, the biomass coming in, what you have is the potential for net zero synthetic chemicals and fuels and feedstocks being produced in the region. You're leaving open the possibility, and you're building the infrastructure that allows this to happen in the future. And you've got the means to get the CO2 out to sea and into a deep reservoir if you need to. So what you're making possible, not guaranteeing, but making possible, is that Prince Rupert is in the same position as Rotterdam, Teesside, Bergen. It's these European cities that are planning on building out this kind of net zero hydrogen, ammonia, and synthetic hydrocarbon-based infrastructure with the necessary CO2 disposal. And it's not something we have space for in Vancouver.
The other question for both you and Dan is around, I hear a lot in this conversation is the transition from using gas as a fuel that involves combustion versus you either have a new way of producing gas, either through bio and other sources. So there's a substitution there for a fossil form of gas, but also gas is going to different places around the world to produce products, and there actually isn't a combustion involved.
Yes.
And there's actually the ability to manage the CO2 in a way that isn't being released into the atmosphere, and actually be a product or it ends up being sequestered. And that's the decarbonization. Gas is still used. it isn't combusted.
One of the interesting opportunities there is that in North America we use gas and what are called pentanes plus. It's chemicals that are just a couple of steps up gas to make chemicals and what have you as feedstocks. Other places are forced to use coal. A lot of this done in China. And what if you can get LNG to them, it allows them to step down from the coal and use gas instead as a chemical feedstock.
It's Alex, it's Rob here.
Yeah.
Maybe just to provide another resource for that graphic interpretation request, which is a pretty big request, I think, to distill it into that. But Chris did refer to the shell sky scenarios. And if I'm not sure who's doing the graphic interpretation, but if they go to the Shell website and find that sky scenario, they'll find some really interesting graphics, exactly what we're talking about. And the graphics sort of start, here's where we are today, and here's what it looks like, where the CO2 goes and all that sort of thing through our energy system. And then it shows a different graphic, for every, 10, 20 years out into the future to get to the point where you get to this net zero carbon in 2070, I think that particular scenario talked to. And so he might find some very good concepts there to help him with that graphic interpretation.
That sounds great. What is the website again?
Sky. SKYU. Yeah.
SKYU?
It's Shell. It's the Shell. It'll be www.shell.com. But then inside of that, you're looking for something called the Sky scenario. SKY. Scenario. Under probably the
Isle of Sky.
Yeah.
Okay, Adriana will make sure that she has access to that. Great, thank you, Rob, for that suggestion. Go ahead.
Sorry, Chris, I just asked you, why is Europe so advanced, I guess, in this regard? Was there government incentives that were put in place, or is the private sector doing this economically on their own?
There's a lot of reasons for that. They're running out of North Sea gas.
Mm-hmm.
They have been for a while. They don't want to be dependent on Russian gas.
Mm-hmm.
There's all sorts of complex. Equinor, I have to say Equinor it was Statoil, it was a Norwegian state oil company, is very far thinking. Like, they're in the business of making money for the Norwegian government, but they were the first to experiment with CCS on platforms for formation gas, CO2. They've been doing all sorts of post-combustion experiments, what have you. And even Shell, based, it's a mix of UK and Holland, like there's a whole section of Shell that looks at these scenarios, and they offer them to the company as one option should policy go that way. But again, they're not a huge oil and gas production region, so access to oil and gas is always a security issue for them. So to the degree that it can depend on domestically sourced renewables, which is why offshore wind has gotten such a kick, why nuclear got such a kick in France, that it's just a completely different political economy environment.
So then, on that basis, then for that transition to take place in Canada, there would likely have to be policy-driven or government incentive-driven, since we don't have those same challenges that would drive that outcome.
Yes. Yeah, we don't have natural constraints, the same natural constraints they do. And it's interesting too, like the UK has managed to achieve bipartisan support for climate policy. So, and they've got a long-term planning agency called the UK Climate Change Commission that looks at these things from a long-term point of view. And you get a little bit of swing between Conservatives and Labour, but there hasn't been much over the last 20, 30 years. It's not a football between them, which is kind of where we need to arrive in Canada. And then it's just not much of a question in mainland Europe. You don't really have a lot of climate denial going